All right, welcome everybody to Radio Telescope Observation Party for May. A couple announcements. Sign up for the online or if you're going to actually physically go to Green Bank. Deadline's approaching fast. Please sign up now so we can make arrangements and get all the links made, and definitely with travel arrangements and food and everything if you're going to go. We have an election going on. I still have nominations. We need, right now I've got 3 out of the 4 board members. I've got at least one person. 3 out of the 4 board members are going to reapply. So I need one more board member. If you want to get involved in what we do, you get a lot of things happening with the board. Please nominate yourself and just send me an email. We also have the secretary and the assistant treasurer positions that are open. Those jobs are important, and to have somebody who's willing to spend a little time improving those jobs and documenting everything we do at Sarah. Okay, that's all I've got. Ted, why don't you start off?
Thanks for number 1 here, but I have nothing to add. I've been working on a bunch of projects, but nothing to report yet. Thanks.
Okay, thanks, Ted. Let's see, Edward.
Hello, can you hear me?
You can, go ahead.
Yeah, well, I don't have anything to report either today. So.
All right. Okay, Dmitri.
Hi to all. I have some information about April observation of pulsating maser. Just a moment.
Okay, we can see it.
Do you see the screen? Okay. This is a pulsating maser I already reported about its observations. G107 for code for short. I reported 1 month ago about observations in line 6.7 gigahertz in methanol. There was initial mistake in expected observation dates. First one March 11, 12, 13, but it was mistaken observation data. I expected maximum 12 March, but calculations, accurate calculations give maximum in 10, 11 March, and I observed peak maximum in 11 March and lower levels in 12 March. 13 March, I didn't expect it. I didn't detect it, this maser at all. This behavior correspond to the detection of this maser. New observations was already without errors in expected dates of observations 13, 14, 15 April. maximum at 14 April. Observations definitely higher than minimal detectable peak flux density, 57 Yansky up to 100 Yansky. I don't know why this line is splitted into lines. 15 April, some similar under the noise, minimal detector of peak flux density is observed, but this is under peak under level of noise peaks. So these results correspond to observations, correspond to detection of this maser. Uh, months ago I've tried some estimations about possibility of detection in hydroxyl lines of this maser,
Oh
but
dear.
they are very weak. 1 to Yansky. It needed long observation time and needed 20 Kelvin of system temperature. This is observations for 20-meter dish in Green Bank facility. My I've tried to some observation of my hydroxyl masers in 20-meter dish. And problem is system temperature of problem of system temperature in these observations of this dish. Moon mapping in 2080. This is not my data. This is old data. I've checked it. I've checked the. This is observations of the moon, mapping of the moon, and I estimated levels of P on peak here and levels of floor of noise floor and using calibration info. This gives correct system temperature about 30 Kelvin, 35 Kelvin. But my observations of red supergiants in hydroxyl lines NMR Cygni and VY Canis Majoris in March gives not too good system temperature. This is already post-processor data. Blue shifted this red supergiant usually give two lines, blue shifted and red shifted due to movement of the cloud. You can see blue shifted line is usually stronger because it's from molecular cloud before supergiant, and red shifted line is behind comes from cloud behind supergiant itself. It's weaker. Level for blue lines is peak of blue line is unexpected. Level about 1,500 Yansky, but my estimations and calibration data give very high system equivalent flux density and very high system temperature, more than 450 kelvins. It's a very huge system temperature and give not a possibility to detect weak lines from G107. Same situations in second observation of NML Cygni, peak at expected level, 1,600 Yansky, about 500 kelvins. Same situations for Canis Majoris observations. Red shifted line and blue shifted line are unexpected levels, but again, very high system equivalent flux density and almost 500 kelvins in system temperature. I don't know why from so high system temperature from this facility. That's all for now. If some questions, I will glad to answer.
Any questions?
Uh,
The system, oh, go ahead.
Dmitri, did you write the LabVIEW VIs? Do you write
Yes,
the
yes, yes. This is post-processing program written in LabVIEW by me, and this is window from LabVIEW VIs. That's right.
Okay. So I think it automatically calculates TSYS then, right? And aperture efficiency.
Yes, system temperature from calibration data, as you can see. Just a moment. From calibration data, calibration info. This is not. This is wrong. System temperature mark here. And calibration info. I use calibration info, decall and tcall, and estimate and have estimated for level of floor, and using decall and tcall, I obtained the system temperature.
Got it. Okay, thanks. Any more questions for Dmitri? Somebody's coming on. Anybody? Okay. All right. Thanks, Dmitri.
Okay, thank you.
Rob Lucas. He's in Australia and probably early in the morning.
Very early in the morning. Anyway, I'm like Ted and Edward, working on lots of projects, but nothing new to report this week.
Okay, great. Thank you. Let's see. Don Latham.
Hello to everybody. I have nothing new.
Okay. Adrian. Nope. Okay. Michael Saffer.
Hello, everybody. Talking from Paris. I don't know the weather over in US, but here getting very bad. It has been very, very hot last week. So I will show you some where I stand. Do you see I can see my presentation. I'm ongoing H1 detection with easy array, thanks to TED. So I'm already at 82 drifts. So I accumulate data. So far, I reached 230,000 samples. And so I feel the data. You can see the data. Here is a map. And here I have a question to Ted, because the more I go, the more I get some signal out of the galactic plane. So I don't know the reason. So maybe, Ted, you have any explanation on that? Because you can see this red spot on the south direction of the galactic plane, which I didn't have before. So I have a question. Here is filling my my map of the galaxy, and I can suspect I see 2 3 arms, and some data on the gas velocity and the mass of the galaxy, which seems reasonably accurate. And still I am, so maybe some people can help, because I see that I have, the last weeks we had very high temperature, and I can see that I have very weak signal in the day, and rather a good signal. We can detect signal on the night when it's cold. So maybe it's normal, but maybe you can, some people can give me some answer. I did compare some data from end of early November last year and now. And for the same latitude, you can some declination. You can see that the signal in early November and October was much stronger. So maybe it's just the temperature. Maybe some people have some answer. That's all for me.
So, Ted, did you have any comments on that? May have lost Ted. All right, Michael, that's really good. That's I need you to move south somewhere, get some more southern
Yes.
data.
Yeah. I need to move to Spain, south of Spain or Morocco.
Well, you may not have any power to use down there, so you be careful. All right.
Thank you, Rich.
All right. Great work.
Thank you.
Let's see. Let's go to Helen.
Oh, no, I'm still here, still trying to learn all I can.
All right.
That's about it. Thank you.
Nice to have you with us.
Thank you.
Jack Gonsel.
Yeah, hi there. Jack Gansel, actually.
Gonsel, I'm sorry.
No problem. I don't have much to report. I've been working with Alex's design of the disk Yagi and doing drift scans at increments of 10 degrees of declination and collecting data on that. Getting some good stuff with the H-line 3D Reinhard graphic stuff. Really, really pretty looking data. But at some point, I want to start mapping it across the galaxy, like Michel is doing in France. I don't know if this is a venue for talking about SID as well.
Sure.
I've been doing playing with some SID stuff, and I made a SID receiver, kind of from some op amps and whatnot, to monitor the station in Maine, the Cutler station that broadcasts to submarines. And feeding that into a little Arduino, the data from there to an Arduino, and also put together a 3-axis magnetometer to measure the Earth's magnetic field. That also goes into the magnetometer. And let's see if I can share my screen here. Maybe it's this one. Yeah, can you see that? Should have a graph.
Oh, here it comes. Yep.
Yeah, okay. So I also wrote a program that runs on the PC that takes the data from the Arduino, and in this case, I'm getting a data point about every 3 minutes because I'm averaging about 1 million data points to quiet things down. And in red, you can see the SID data. In blue, this is the z-axis from my magnetometer. And I'm not displaying this right now, but with every data point, I also go out to the USGS magnetometer in Virginia, which is near me, and plot that. And I've been recording this data to a CSV file since December. So I have about 50,000 data points. But here's an example. You see the SID event right here, which time correlates really well with these magnetometers across, I guess, mostly in Europe. So anyway, I'm collecting data, not doing a whole lot with it, but other than having a having a lot of fun with it. So that's pretty much it. And I don't know how to unshare.
Well, that's good stuff. Let's see. I think I can help you there.
Let's stop share. There we go.
I just
Yeah,
did that.
there we go. Okay.
That's really good stuff. And the magnetometer and the WIT up in Alaska does a lot of that stuff with the magnetometer. And you might look at some of his YouTube videos on that.
And who is that?
WIT. Oh, I got the last name. WIT.
Okay.
Whittam Reeves.
Okay, I'll Google it. Thanks. I appreciate it.
Yeah, he does a lot of work up there, and he also does the HARP stuff up there.
Yeah. Oh, okay, yeah.
Let's see. Okay. Now, oh, by the way, we just got some emails from the people at Stanford that are doing the SID program, and I guess they had a glitch in either funding or something, and they're going to have to shift their whole server, the data, to another system. And right now they've got some graduate students working on putting that together. So there might be a glitch in the whole SID data collection system. So stand by. Normally with a SID system that you get from us, actually, the software will automatically record your data onto that server every night if you got it set up right. And then you can actually see your historical data on that server. So there might be a glitch in that depending on what's going on. So I think that's in progress. I don't think there's a glitch yet, but if you see something, know that there is a transition going on. Okay, Alex.
Hey, good afternoon. I don't really have anything. I can, let's see. Well, you can look at my, here's the image. I've just been putting this together over the past couple of days. This will wind up being, let me stand up and so you can see it maybe. This is a lightweight variation of the Yagi. It'll be 1.3 meters long, and it's on a fiberglass core, fiberglass tube. So it's lightweight. So the standard Yagis that I had been that's on the website is 3/4 of a meter. This is 1.3, and so it's nice and lightweight. The other ones, the original ones used 3/4 inch, 3/8 inch stainless steel rod, and they were heavy. This is still based on the light directors, the light aluminum, 20 thousandths aluminum. So it's just another variation. A little bit narrower bandwidth, and it uses the insulated spacers. That's it.
Well, I want to congratulate you on getting the British to form an H-line group based on your work. You got any info on that? Oh, maybe not. Alex,
I think that was Andrew.
Yeah, I agree, but it's based on your work. So
I wasn't aware of that.
yeah, they're basically using your H-line work, and they have a forum going on using the H-line all the H-line work you've been doing.
Okay, didn't know that.
Yeah.
Thanks for the feedback.
I know all this stuff shows up everywhere, so it's really good. Let's see, Paul.
Hello, Rich. Can you hear me okay?
And fine.
Okay, so I have this raster study work that I've done. Um, if you think this is an appropriate place to present it, I'm looking to get feedback on artifacts in my approach and how to interpret the data, if you think this is the right place for it.
Go ahead, Paul.
All right, I'm going to try presenting it. I haven't had much luck with putting it in presentation mode, so I think I'm just going to not do that. Let me see if I can get this thing to show up. Is that showing up for you?
Yes.
Okay. So, all right. So what I wanted to do was to try to use the beginner's antenna, which is all I have right now. It's basically a scope in a box approach. And I mounted it on a Celestron AVX mount, which is a go-to mount. So I could control the position of the antenna. What I wanted to do was to do a raster scan of a relatively small area, which actually turns out to be about 30 by 30 degrees. This is the setup that I used, if you can see this. So what I do is I start out by using a guide scope, and I use this SharpCap software to go to whatever object I'm interested in. Like, for example, if I want to center on the Orion nebula area, for example. So after I've got that set up and calibrated, then I replace it with my radio telescope component, which I built on a Vixen mount, so I can just swap them in and out, and the alignment of it is pretty close to the axis of the guide scope. So that makes sense. That's how I'm trying to collect the data. And so what I did was I wrote a bunch of software to do all this work. I wrote some software that controls the mount to do the raster scan using this ASCOM alpaca interface. And I wrote some software in Node.js and scripts and so on to be able to do the raster scan. I collect the data using, I tried a few things. I started out using the EZRA, but I had some problems normalizing it. And Alex had suggested that I try using the IF average, and I actually wound up having some better luck with that for this purpose. For doing the analysis, I wrote all of the software from scratch. I'm like Java programming, so I wrote programs to do all that. And what I did was I wrote, so I'll just jump to this here. This is, I did drift scan work previously, and I used that work to validate that it looked like my analysis was working correctly. So I'll just, if you don't mind, quickly go through the drifts work, showing it analyzed with the software that I've written. And this is just, a single drift scan. This one was collected. Actually, this particular one was collected with the EasyCal, and it looked pretty good. I have, see this one here. This is actually just showing a comparison of an EasyCal scan and an IF average scan of approximately the same location. And so as part of the work that I did, I wrote a bunch of software for doing filtering and noise removal. I'm in a suburban environment that's really noisy, and rather than, or as an alternative to struggling with trying to electronically remove the noise, I used digital techniques. And that's part of why I want to present this, because I want to get people's opinions on, the validity of what I'm doing. So this is just an example of that. Let's see, go down here. This is, these were 5 drift scans I did at, I think it was like 30, 40, 50, 60, 70 degrees of elevation, 24-hour drift scans that were captured with the EasyCal. On the right side is using TED's software to plot the data. On the left side is my software basically doing the same thing. They're slightly different. I did some extra digital filtering on the software. I think that, cleaned it up a little bit more, so it looks a little bit different. But you can see the results are basically the same. So I'm hoping that this means that my basic approach is reasonable. I guess before I go further, is any comments before I get to the next phase of this, the raster work? If not, I will go on. One of the things I was able to do in the software, and the software, by the way, the software package I wrote, I called RAISE, which is a Radio Astronomy Interactive Study Environment, just to give it a fun name. And you can see on the screen here, there's lots of different options for things you can do for picking data sets. It understands EasyCal and IF average data. And I also have some special methodology that I use for doing the raster scan work, because I needed to be able to coordinate. When I'm doing the IF average, I have to take a continual stream of data. So what I do is I have to record where the antenna is pointing while I'm collecting that data, and then I have to match that all up later, and this software does all of that as an option. In addition to being able to do displays of drift scan, it will do the raster scan, which I'll get to soon. One of the other things I did was I tied into this software. There's a GNU plot, which does a lot of nice 3D plotting, and I was able to automate that. So what I can do is I can, pull in the data, analyze it, and then I can actually have it fork off an executable of the GNU plot. And you can see this is an example of that those raster sweeps that's done on a 3D plot. Okay, but let's see. I also did this work as well. This is doing the frequency spectrum sweep, and this shows on the top there's one of the average sweeps that you typically see. On the bottom is one of the frequency plots of the same data. It's time aligned. Let's see what else I got here. This is actually just the same frequency data plotted in 3D. This one here, this is showing, okay, so one of the things that I've been struggling with, and I'm hoping I'm getting it right, is doing the VLSR adjustment. This is an example of one sweep with raw and VLSR adjusted. I tried a number of ways to do the calculations, and including asking ChatGPT to give me a function. Ultimately, I wound up getting, I think, better results. I took some of the code, Ted, I hope you don't mind, from your program. I found a few lines of the AstroPy. And so what I had to do was, because I couldn't find any good libraries for doing this kind of work in Java anymore, they used to exist, but they're not supported anymore. So what I did was I created a pipe from Java into Python, and I'm using AstroPy for doing the calculations that AstroPy is good for. Let's see. All right. Again, if anybody have any questions before I go into the mosaic part now?
If that was really VLSR corrected, you'd probably see a straight line. You're still seeing the rotation of the Earth in that data.
So that's why I wanted to, present it here, because I thought so too, but I was struggling with trying to get the calculations right. And, one of the things I hope to gain is that maybe some of you guys can help me out a little and see if I can figure out how to get the calculations right, if you wouldn't mind. Okay, so I'll go on with the raster work. This is a data matrix showing the points that I collected. It's a 7x7 matrix spaced at about 4 or 5 degrees. And this is just a form of the display that I have that shows the various data characteristics. This is the data actually, and on the left shows the individual samples that were collected. I collected about somewhere 6, 7, 8, 9 samples per point, and that's on the left. On the right is the average of those points, and I did do lots of corrective calculations, which I'll explain, and which certainly are open to your criticism. But this actually shows a slice of the data. It's just in magnified form. I can go through and I can either do a horizontal or a vertical slice through that matrix and show them as a waterfall and blown up. And you can see on the left, on the right side, there's a heat map version of the same thing. Let's see here. Let's see. Now I'll get into the really nasty stuff, which I'm sure you guys will have plenty of complaints about. Hopefully you can set me straight. So up in the upper left corner is the raw data. Not very pretty because, like I said, in my environment, it's not a RF friendly environment. So what I did was things like boxcar smoothing. I actually have something where I can specify frequency ranges to chop out and do a linear interpolation between them, like small sections of the frequency range. And I can also do averaging in various ways. Like if I'm doing a waterfall, if I wanted, I could do successive averaging. That's in the upper right-hand corner. You can see an example of that. This is not the raster per se. This is looking at it as time series data, because when I collected it is a time series. And as I said, what I have to do is I have some metadata that where I record the start and stop times, which I get from the mount. So what I do is I give a command to the mount. I tell it to go to a location. It comes back and it'll tell me when it's stable, and then I record that time. And I'll collect, like I think I collected like maybe 2 minutes worth of data at each point. I can't really do too much more. I can only do about a 2-hour study per night, practically speaking. And it didn't seem, I don't think it mattered very much anyway, because most of my noise was terrestrial RF or maybe satellite or airplanes, I don't know. So the signal averaging doesn't help much with that. The signal averaging is really good if I had Gaussian noise that was because of the true hydrogen signal. So this is just shows an example of kind of more rawish version of the data, and you can see there's some ugly things in there, and I can manually get rid of the ones that are clearly seem to be contaminated by noise. And so what I do is I manually remove the bad ones, and then I do the averaging. And this is what happens after that. And I have a few different ways that I've done the normalization to get rid of the curvature in the spectrum. In some cases, I used the background function in IF average. In one case, something went wrong, but I did have the reference signal that I was using, which was a 50 ohm resistor. So I subtracted that calculation later, got pretty similar results as to what I got from when I had the background subtracted data by IF average. I could do other things too, like I could, well, let's see this one here. Yeah, so the difference between these. Yeah, this was the, after the baselines, or correction, or the IF average, whatever it looked like. You can see there's some tilt on the baseline, so I did a 2-point flattening. And then I could also get rid of everything below 0 before I would do integrals. Okay. Right. So this just shows okay. So this will certainly be a point of discussion. This is where I could especially use help. Is what I do is I can set frequency bands to look at, which presumably have to do with the velocity of different parts of the sky that I'm looking at. And, it's a matter of trying to interpret what these things mean. But what I did as a simple starting point was to band these things and make the assumption that I could ultimately understand something about the differences in the motion of the H1 that I was looking at, and put it into a graphical form. And let's see, this is just showing a blowed up version of being able to select frequency ranges. And this is what my ultimate goal was to try to make something that looks like I took a picture of it with a CCD camera, and pseudo coloring for frequency, kind of in the same way you would do as if you had optical filters and you were doing monochrome recordings with astronomy, light astronomy. This data was centered on the Orion Nebula. I have an inset there. You can see there near the middle. It's a picture I took of Orion. It's not to scale. The data that I collected was over 30 degrees, and that Orion picture is like, that whole thing is like 5 degrees. So it's like one box out of the images you see. And if you look on the top and looking across there, you can see different kind of presentation modes. The first one is the raw, where I pseudo-colored those bands. In this case, I think I just had 2 color bands. Then I smoothed it, just digital filtering, just to make it more viewable. And then the next 2 are just showing the bands in isolation. I can change the filtering, the cutoff level. It's sort of the same things you do. Anyone who's done optical astronomy, that you can like set the black level. It's effectively the same thing here. And let's see, in the lower left, you can see I have an inset which shows on one of those maps that I borrowed from TED. It shows where that data was collected, and the upper one, the lower one, actually shows the sample points where they were taken. Towards the middle section, there you see there's I have plotted in 2 different ways where the antenna was pointed in elevation and azimuth, and I did it in 2 different ways. The upper one is like having taken an instantaneous snapshot. If I was in the center and I took all points at once, and so you see, because I was pointing the antenna in RA, not alt-Z coordinates, when you convert from RA to alt-Z, that it's not going to be a linear square. It's going to be distorted. The bottom circle is representation was the alt-Az coordinates of the antenna as they actually occurred. What else do I have on here? There's a waterfall version of the spectra. That's a time series. The far right center is actually a heat map version of that data with where all of the where both frequency bands were just summed together. Let's see, what else do I have? And I tried this a few times. This one was centered on Orion. No, I'm not claiming that this is a necessarily Orion. This is the H1 data around Orion. I'm hoping that you guys can help me determine whether it's actually possible that I could have detected any of the nebula that I was aiming at or not. I'm inclined to doubt it with the antenna that I have, but you'll tell me. This one was on Crab Nebula. It was same kind of study. And let's see, what else did I have? Cassiopeia, I centered on that one and ran a study. And what else did I do here? Heart Nebula, I centered on that one. And let's see. Oh, this is all of them together, just showing where they were. I'm not really sure what my resolution is. I'm assuming that I'm getting somewhere in the range of 5 degrees with this antenna and in the way that I'm going about doing it. In part, that's based on the fact that if you look in the center lower, those are just some blow up of the drift scans that I got. If I wasn't getting 5 degree resolution, I don't see how I would get a curve like that, because you wouldn't see a shape. It would just kind of just be flat, I think. But you guys you'll help me out on that as well. Let's see. Oh, this was a little hard to see, this one. I tried to plot, there are lines, if you can see them sticking out, green, red, and blue lines, to see where I'm cutting across the arms. Again, hopefully I've got this right. I'm relying on calculations that I need to verify. And let's see, so that's it. So really, where I stand now is I need your help in knowing whether I'm going about this right or not, and where I have, errors, and where I could make things better, and what to do next. So I will turn it back.
Wow, Paul, you have been busy. I'm impressed. All kinds of things going on in there. As far as using my code on the VLSR, yeah, please. That's why I post it there. Let's all improve Sarah's capability. I think you're doing great stuff. And let's see, on VLSR, I agree with Alex that it should be a little flatter after the VLSR correction. And good luck. It took me a while as well. But once you
I was hoping for a little more help than that, but okay.
Well, we can talk about details. I don't know what you have. You see what I have. We'll figure the thing out.
Okay.
It's just figuring out how to use AstroPi the right way.
So it's very isolated. The AstroPi code that I'm using is a very small piece. I can easily show it to you. Because what I do is I just created a pipe from Java into Python. So
Right,
all it
yeah.
does is just stream the data in, and it streams the results back. But the code is pure AstroPi code, and it's very small, and it should be very close to what you did, except if I messed it up. So
Well,
maybe
let's take some time offline and figure that thing out. That'd be cool. I'm impressed that you have to get over to the library in Python, but yeah, okay. There it is. You're tying together so many things. I think it's exciting. And the central part is all Java. Is that right?
Yes, it's Java, and so there are some issues. Like I prefer using Linux. I'm not really a big Microsoft fan, but I do use it plenty. I did get it to partially run on Windows, but the GNU plot stuff won't work. and I'm still struggling with getting the Python thing to work. I'm pretty sure I can get that pipelining to work, but I didn't quite finish it yet.
I had all of COVID to COVID to develop my software, and here you're doing it actually during real life. I think that's fun. So once VLSR is adjusted, we'll say properly, then yeah, that'll change the frequencies around, and of course that'll change what your filters show in red and blue shifted, and so yeah, maybe that's going to change things dramatically for you. But you present the data in lots of different ways. I think that's exciting. But other folks may have comments as well.
Well, I have a question on the way you capture the data. If I understand you, your antenna is on the equatorial mount, and you spot, you make different position of your antenna, but do you keep it drifting during each cells, or
So good question.
How do you collect the data? I
So,
didn't understand very well.
Good, very good question. So I've tried a few different things. So at first I was concerned that the motors in the mount were generating RFI. So I actually made it so that I could command the mount to stop tracking during the collection. The collection period was only 2 or 3 minutes. So the drift is so small compared to the, to the antenna aperture that it was not a major issue. But I have tried it both ways, and it will work either way. And the mount, what the mount does is when I turn it back on again, even though it wasn't tracking, it knows where it is, and it jumps to the correct position.
Okay. So you scan spot by spot the way you show in one of the figure. You have several points, and
yes,
you scan in both position. Okay.
And as I said, it's in RA coordinates. So it was kind of funny when I first started to do this. I talked to the people who developed the ASCOM alpaca code, because I was trying to get my code working, and they're all optical astronomers. And the first thing that they did was give me a tutorial on how it's just, the images I'd be getting were distorted. You have to be careful not to think of them as being like linear images. And that's why I made those plots to, just to show that I was aware that it's a little bit disingenuous that to show these as linear images, because they're only linear in RA coordinates.
Thank you.
I have a couple questions as well, if that's okay.
I was hoping you would. I was expecting you to say something.
Yeah. So first of all, I think this is really great work. Like you are already on quite an advanced level.
But not understanding the data. That's why I need the rest of you guys to help me.
Yeah, no problem. So one thing I was wondering, so for the drift scan and for the also for the raster scan, so do you do the VLSR correction for each point?
Yes. I don't know if I'm doing it right, and it's probably could have a session of discussion just on that. And as Alex pointed out, there's reason to be concerned that I have calculation problems. But yes, I attempted. I knew that the exact time. I knew the RA where I was, and I tried to use the AstroPi software to correctly calculate it. But I'm not convinced I have it all perfectly right. I'm still struggling with that.
Okay. So another question. So what's your dish size?
It's the scope of the box. It's a 1 meter, one of those, what's that company that makes these things? It's off the shelf. Noelec, yeah. So it's all Noelec. It's a Noelec dish. I'm using their H1 LNA. I'm using their version 2 SDR.
I just wanted to know the size because this determines the resolution.
Yes, indeed.
Because you mentioned it was around 5 degrees, and I thought that was really unrealistic for 1 meter dish because I'm getting 5-degree beam with a 3 meter dish.
So good. So here's my reasoning, and this is what I want you to argue with me about. I view this the same way that I view doing optical imaging, which is that if you move the baseline up and you take just the highest points of the signal, that I would argue that you will get higher resolution, just like you get less fuzziness when you do that with an optical image. But you guys probably will say, I don't know what I'm talking about. And that's what I'm hoping to hear from you.
Well, actually,
yeah,
I would.
I was thinking from oh, sorry.
Sorry.
Go ahead.
I'll let you continue. Sorry.
Yeah. I was thinking, like, from a physics point of view, like your resolution is limited by your collecting aperture, essentially.
So I have a question for you. So
yeah.
this is my reasoning was that if I can see curvature in those averages, in the these, like, just looking at Ted's diagrams, that why can I see the curvature, which is that curvature would require much greater than 5-degree resolution? Why can I see curves if I don't really have that resolution?
Let me throw in my 2 cents. In the 1 to 1.2 meter class systems, the minimum detectable time is around 4 minutes, which is 1 degree. I would question if you would specify that as resolution. It certainly isn't beam width, but I'll share a couple photos or scans with you, and you can figure out what that means from maybe a couple of these things. So, yeah, minimum detectable is probably down in the 1 degree range.
That was my impression, but again, that's why I'm here. I'm hoping that you guys will argue this out and help me understand it. My impression was that I'm doing around 5 degrees, maybe a little better, but that was a little surprising considering how small the dish was.
I think it's physically impossible. Sorry.
I don't disagree with you, but I just don't understand the results otherwise.
Yeah, we gotta understand that there's a difference between the half power beam width of the antenna and the ability to detect slight differences
Exactly. Yes.
in smaller changes in position.
That's my point. Exactly. Yes.
So yeah, because the half power beam width of your antenna is probably like 15 degrees or something, or bigger than that even, with a 1 meter dish. But you can detect smaller changes. It's just not going to reject. There's going to be smearing, right? There's going to be bleed over from the adjacent positions.
Again,
but yes, you can detect smaller.
Is it reasonable to think of this being as analogous as the kind of manipulations you do in optical astronomy, or am I thinking about it wrong?
Can I toss up a slide and you can draw whatever conclusions you want from this? If you would stop sharing for a minute, I will show you.
Oh, I'm sorry. I thought I did.
No,
hold on.
I will show you a set of scans taken at 5-minute intervals, which means 1.25 degrees. Let me see.
Do you have control there? I don't think I'm sure.
I don't know. Yeah, maybe I do. Let's see. I have no idea if you're seeing this or not.
Yep.
Is it large enough to see?
Yes.
Yep.
All right. So this is a drift scan. This is the peak value that I always go to, DEC 40 at RA 2030. And so these are at 5-minute steps. So call that as you wish. Okay. I mean, I can detect 1 degree steps with a dish that of the size you're talking about. So
yeah, I think Jason Burnfield summarized it pretty well. So of course, like, you have a limit with your beam width, but you can still, like, because like you should think of the beam of the dish is not like a solid square, so to speak, but it's like a Gaussian. So it picks up like maximum amount of signal at the very center, and then as you go like off the center, it's kind of like tapers off. So you can see like differences that are like much smaller than the actual beam width, but you just get like a lot of bleed over from like adjacent areas.
And that, but isn't that like the same thing in optical astronomy?
Yeah, I agree with
absolutely.
you.
I
think
believe it is.
we mix resolution and the average signal. The average signal is integration and it can go down, but resolution is different. It's the minimum distance you can separate two signal. I mean, so you are. I agree with you. In optical, you have the same. You can detect variation lower than the resolution of your instrument.
Yeah, in actually coming up at the Eastern Conference, if you're attending that, Andrew Thornett and I are presenting some spatial mapping that we did of Doppler velocity of M31 and M33 using the 20-meter scope at Green Bank, which has about a 3/4 of a degree half power beam width at L band. So and that's roughly the size of M33, but I was able to map spatially separate points of Doppler because of the fact that you can detect differences within that beam width. And I first saw this done in Jean-Jacques Montois' paper back in 2018 when I was first trying to detect those signals, and he actually used his 5-meter or his 5-degree beam width from his 3-meter dish to map several points across the disk of M31. And even though the beam was as large as the beam width was as large as the whole disk of M31, he could still resolve details within that because, like you said, resolution is not the same as beam width, right? So, yep.
Here's another slide to give you an idea. This is what your telescope is actually seeing. Let's see. This looks something like that, okay? Just one fuzzy pixel. But what that's saying is that integrated brightness can detect shifts in, about 1 degree increments.
That's the way I was thinking about it. I was hoping that I wasn't misinterpreting things because, like I said, to me, it seemed analogous to the kind of things you do to get a nice image in optical astronomy. And I actually, one of the slides I had there I showed was actually the data from the manufacturer that shows the shape of the gain distribution, those typical things that they show for antennas. And it looked sharp enough that I thought that it would be possible to do what you're showing.
Yeah, I think you're on the right track with what you're.
Yeah, I had a question for with now we've got Jason online too. Is if you tried one of the like Andromeda and with a raster, you might be able to pick up the whole system as opposed to like Jason, you have problem getting both sides of it.
Yeah, the problem with that small of an aperture is the signal size of Andromeda is so tiny with that aperture. I think it's going to be nearly impossible to pull it out of the Milky Way. When I think it was that's the other paper that Edward and I are jointly presenting at the Eastern Conference is using the lab survey data to simulate drift scans of extra-galactic sources, and what we were able to see is kind of what the relative signal strength is for various beam widths for these objects. And I think getting below about 2 meters, you're not going to have enough signal to pull out.
That was
I was
a
even
question
trying.
I had. Can I ask you, with the images that I had there, the objects I was going after, I was assuming that with the antenna I have, I couldn't really pick up extragalactic sources. Is that true? Is everything that I have likely to be just the galactic hydrogen?
Yeah.
I believe so. The galactic hydrogen is going to be dominating that that picture. Yeah,
Yeah,
it'll
I
be
mean,
100 times.
Yeah,
Because
even
your
like I
image is
had
blurred, because your image is blurred over that 15-degree beam width. You can't see little objects. It's like the sun isn't particularly strong with with an antenna being that broad, where it really has a lot of energy, but it's only taking up a whole fraction of that beam envelope.
So none of the objects like I have, like even like Cassiopeia, even that is not strong enough that what I'm seeing in my image is probably not actually Cassiopeia. Is that
No,
correct?
no. There's actually another complication here, and that's that the objects that you are referencing here, they are continuum sources mostly. So they emit like over a very broad spectrum, so not just on like the hydrogen line. So what you're seeing mostly is like just the hydrogen line in just like the galactic plane. And yeah, in order to detect the continuum radiation, it requires a different approach. You have to like measure like the backgrounds like outside of the hydrogen line.
Okay, that's what I kind of figured as much. I was centering on these objects, but I wasn't quite naive enough to think that I was picking them up.
Well, yeah, the reason why you don't really see a hydrogen line emission from those smaller stellar sources or stellar neighborhoods is because you need a lot of hydrogen to have any signal, because that signal is very weak. The transition happens so rarely. I think it's like once in 11 million years or something for a single atom. So, I mean, you need a lot of hydrogen to see any signal at all. So really the only sources you're going to see an emission line from neutral hydrogen would be something the size of a galaxy.
Right. Well, I mean, I was pointing at some galaxies too, but there again, what I was doing, what I did was I was looking at that map of TEDs and looking at high emission sources. So I figured, well, let me try centering on them.
You want to take a look at the VLSR corrections?
You mean offline to?
No, I got a couple graphics.
Oh, yeah, I'm sure.
All right, this is what.
Why don't we call this in about five? You got about 5 minutes. I'm going to shift.
Yep.
And then you can do it. We can do it after the session. I'll leave it on. You guys can do the detailed stuff.
2 minutes.
Go ahead, Alex.
This one. This shows you how dramatic the background shift is, the velocity shift over a 24-hour period. Okay. Now, let me show you a correction. Okay, this, I don't know if it came up or not. I'm still getting an hourglass on the time. This is the VLSR correction curve, and it's almost plus or minus 40 kilometers per second. This is that same data corrected. Okay, a nice straight line. It's a big deal. There's a lot of shift that's associated with the velocity over a 24-hour period. That's my story.
Okay, well, I'll have to get in touch with you and see what calculations you're using and
that's in
compare it to what I'm
MATLAB.
doing. Okay, well, like I said, I was using the AstroPi, and I don't know if I'm using it right, but that's what I was using.
All right, excellent work, Paul, and look forward to that. And I'm going to maintain this on afterwards. So you guys want to have a session after the RTOP, and won't be recorded. You guys can do as much detail as you want. Well, Jason, while you're on, let's do you.
So I got a little bit of show and tell. As some of you probably know, since I moved to Socorro, conditions aren't favorable for my 3-meter portable dish. It just can't handle the wind. And I'm in a 2-bedroom apartment on an upstairs balcony, so so I had to pivot a little bit. So I tried my hand at building a Yagi antenna using a wooden yardstick and some copper wire. And yeah, I've here's the I don't know if you can see it. I started out with 15, and then when I did some pattern testing actually in my apartment, because I tried doing it outdoors and the weather was just too windy. But I was able to set up a little dipole element, and I used my nano VNA, and I did a quick and dirty scan of the pattern, and this is the result I got. So this was the 15 element, and then I moved it away from the window because that, you see that side, that lobe on the left side there is it was close to my window, and I think it was getting some reflection from the screen or something.
Hey, we're not
I
seeing
moved
it.
it over to the other.
Jason, we're not seeing your
Oh,
show.
shoot. Sorry. Yeah, give me a second. I gotta share my screen. Forgot. All right. Share. Okay. So so this is, can everybody see my screen now?
Yep.
Okay, so this was the first with the 15 element setup in my living room here, and I'm getting this significant side lobe here, and I think it was reflections from the window. It was on that side of the room, so I moved it over to the other corner of the room, trying to get at a diagonal so I could get as much distance as possible from the emitter, and this was better. As you can see, the beam width it's slightly off-centered because I realized what I was using to sight was slightly off. I was using the edge of one of the structural members, and it was slightly off. So, but in any event, you can see the 3 dB point is this green line, and so you can see it's between 20 and 30 degree beam width. These are 15 degree, or sorry, yeah, 15 degree increments. And then this was when I added the extra 10 elements. You can definitely see it narrowed the beam up quite a bit. Yeah, so ongoing, I am getting some halfway decent Milky Way scans with it, but I'm having it's not performing as well as it should with the Milky Way. And I suspect, at first I thought I was getting interference. I had it mounted on my balcony pointing at 70 degrees elevation. And I believe the steel structural members of the balcony were actually interfering with the antenna and causing problems. So I did try a little bit down in the parking lot in front of my apartment, and I still was getting the same performance. So I'm beginning to suspect that maybe my Sawbird is having some issues, and maybe it's not performing as well as it should. I've got to start looking at some of the other components of the system, because according to my plot, the antenna pattern seems to be pretty on the money. So so I don't think the antenna is the problem. Anyway, so I'm trying to come up with a small apartment setup for suitable for my current living situation. Plus, building a new antenna was kind of fun anyway. So,
Any questions? Now, Jason, I'd be interested in, because I think that what you just did there with the antenna, and I know Alex has done it too, but I think that is a core skill we should make for the Sarah group, is that they're able to take an antenna and map it like that. I wonder if you'd just put together a Zoom video on sort of how you did that and what you used for the transmitter and everything.
Yeah, I might do that. So I actually just made myself a protractor on a big piece of cardboard cut out from one of my moving boxes. And I just literally lined it up by sight with I've got it marked in 5-degree increments. I don't know if you can see that. And then my transmitter, I literally just made a quick and dirty dipole on a N-type bulkhead connector, and hooked that to the output port on my nano VNA, and then hooked the measurement port to my antenna, and I had a long enough cable that I could separate them by as far as I could physically get them apart in my apartment. Actually, I adjusted the distance until I got bore sight at 0 dBm or at 0 dB on my nano VNA with the power level set at a certain level, so that I could, that way I didn't have to do a lot of correction. But I found though that when I switched to the 25 element Yagi, its gain was high enough that I ended up not being able to set it at 0. I set it was at +10. I think it was getting so. But in any event, I was able to do the post processing and get a nice antenna plot, and it's actually, I mean, obviously it's not a perfect setup. I've got interference from objects in the room, but it still gives pretty decent result. I mean, I was surprised how well it worked just setting it up in my living room and having the transmitter on my kitchen counter like 10 or 15 feet away. It's definitely once you're over a meter away or so with this wavelength, you're already getting into the far field. So it was definitely working.
Okay, excellent.
Like I said, I initially wanted to do it outdoors, but at this time of year, Socorro is windy, and so my stuff was blowing all over the place, and I was like, okay, I got to do this indoors. It's not working.
Actually, what it is northern New Mexico moving back south. Happens every year.
Yeah, in fact, it was funny when I first got on the meeting. If you noticed, I put my earbuds on for just a little bit. It was because it was raining, and we haven't had much rain until now, and my roof is a metal roof, and it was just loud. I could not hear, so I had to put my earbuds in because the rain was just too loud. But then it kind of quieted down. So
the monsoon season will start soon.
Okay.
Yeah, that's what everybody tells me.
Okay, let's go. Johnny Cox.
I'm here. Can you hear me?
Yeah.
I don't have anything to add. The only thing I've been doing at home is getting some Jupiter emissions still. That's getting fewer and far between, and pretty much daily solar. But that kind of keeps me busy. But that's all I have to report.
Okay.
Thank you.
All right, I got N1LS. I forget who you are. Nils? Nope, not coming on. David Kunzman.
Don't have anything really, just listening. I had a question though. Is the Super SID sort of obsolete now? Or has it changed?
No,
has it changed who runs it?
No, it's still we're still building them for the Stanford group, and the Stanford group is still collecting the data. So as far as I know, all that is still in place. They have to shift the servers out because of the some issue, I think, with funding. But as far as I know, it's still it should be transparent to the users, and the equipment's still the same. You will see other people building their own systems, and that's happened for a long time. The only issue with building your own system is that it may not integrate software-wise into the Stanford database. So that's the only difference there. But it works the same way, probably.
I had one more question. You know that Inspire kit that Stanford has for space weather? Does that measure the same thing as SuperSID?
Not 100% sure. Anybody know have an Inspire system? I think Whittam Reeves has given a couple lectures on that, and you might look up his YouTube videos on that. I think it's different, but I'm not sure why.
Okay.
All right.
That's
Thanks.
all.
Bruce Rout.
Hi. Yeah, just joining in just to listen in. I've got a very old USRP-1 that I'm working on, and luckily there's no software for it, so I have to write my own. And I've been learning a lot, using that. And I'm going to try and set it up to a pair of feed horns. But anyway, that's all I've been doing, and I've just been learning about the software and building my own software for the thing. But thank you. I'm just listening in to hear what others have to say and what their projects are, which is very interesting.
All right. Thanks. Good luck on that.
Thank you.
Let's see. I've got an iPhone. Somebody's on with an iPhone. And Dennis Hoofnagel.
Thank you, Rich. Nothing new to add. Springtime, too many projects to going on. Thanks a lot.
All right. Thanks. Bob.
Yeah, I have a couple of things I can add today. Let me share my screen if I can get this to work. Let's see. I'll just share my desktop. Oh, it may not let me do it here because I'm not. I didn't have all the authorizations set up on. No, I'm going to have to show you next time, I guess, because it's not going to just let me start sharing without stopping Zoom and restarting it. But I've been working on a couple of different things. One is I was going to tell Jack, he was talking about 3-axis magnetometers earlier. I've done quite a bit of work on that. I've had a 3-axis magnetometer running for a couple of years, and I've written software to take that data and plot it. And that was one of the things I was going to show you here. But the data and my program for doing that is on GitHub under N5BRG. So if you just do a search for GitHub and N5BRG, you'll find a program that you can download and utilize for looking at your 3-axis magnetometer data. Mine is based on the Tapper design, and so I've got the comma delimited data files structured that way, and it also lays in a line for sunrise and sunset at midnight because things happen or change or transition during those time frames as the Earth rotates. So that's out there. And then the second thing I've been working on, spending a great deal of time on, is what I'm calling a Muon telescope, which I have some Muon detectors, using the scintillators like Spencer Axion did from MIT. And I've had those operational for a while, and I've written software I'm not so excited about just looking at the little display like he had that gives you the count as you see it. I wanted to be able to record that data. So I've set them up to allow me to scan the data in using I²C. And I've got software now that collects data from multiple Muon detectors. And so then I built I'm building using a 3D printer, a method to have an as-L pointing capability of a pair of those detectors. And my goal is to build 3 of these and have one of them track the sun, which is the dominant producer of muons here. And then the other 2, I was thinking about tracking the T Borealis in case we do see muons when it begins to pop. But I want to be able to do differential comparisons between the sun and the other one. And then the third one, I'm going to just use it for I'll call it all sky collection scheme. And I've set this up, the thing that I've built, with 28 millimeter spacing between scintillators, which is what I understand the British guys are doing in their new system. I have the ability to print a different holder though and change that spacing if I wanted to. And I'm using inexpensive little motors and to drive it. And I'm in the process now of doing the PC board layout. So I had software, 3D plastic parts to build, and there's quite a few of those, quite a few hours of printing, but I'm planning to put all this on GitHub so that as you see it, if you were interested, you could duplicate it. It stands about 10 inches tall, and I've got the one I built mounted on a 8-inch by 6-inch metal plate to hold for weight, just to try to stabilize the base, and collecting data with a Raspberry Pi, a Pi Zero, so it's a fairly inexpensive computer approach. So I'm sorry I can't just share the screen. I'll try to get that straight so that next time I can. I have a fairly new computer and hadn't had to share screens with it yet, and blocked me out for security stuff here.
Hey, Bob, if you go ahead and drop Zoom, come back up, can you get that online? While I'm
Yeah, I can try. Go ahead, keep going, and I'll try to do that.
All right, we'll do that.
Okay, thanks.
Tom, Mr. Treasurer.
Yes, I just basically I am here to listen to see what people are doing, and I just noticed that Bob's screen popped up. So why don't we switch?
I guess it did. I'm sorry.
Go ahead, Tom.
Okay, well, like I say, I just noticed that Bob's screen popped back up. So why don't you go back to him? I've just been listening to see what people are up to. I've not been up to anything particularly radio astronomically related, though I have spent some time offline because I went to a astronomy conference that I'll talk about some other time, perhaps.
Now, is there what are the time limits you want for the Eastern Conference signups?
I believe that that Mark has set that up for the 29th of March, excuse me, of May. So the end of the month is coming up, and I will remind people that you are required to have a Sarah membership to register. But yes, that is coming up. And since I've been offline out of the world, someplace beyond the edge of the internet, I've got a good bit of stuff packed up to deal with. There are several memberships and some registrations, and at least one scope in a box that are waiting in the queue.
All right, thanks, Tom. Go ahead, Bob.
Okay, yeah, I've got the what I call the Muon telescope up there now, and you can see that it's just got a base with a little motor over on the bottom right, and I've got it belt driving the with like a sprocketed belt, the center shaft that's going to set the rotation or the azimuth angle. And then right at the very base of that, I'm going to use a magnetic pickup that's going to be reading the angle. And supposedly these things are good for 1/4 degree. So that's part of the whole project, is to try that out. I have worked or helped develop magnetic sensors in the past, so I have a little background in that. And then you can see the elevation motor hanging off on the right-hand side. And then on the left is a place it's going to hold the magnet. And I've still yet to build a little bracket that's going to hold a PC board with the magnetic sensor that's going to face that magnet over here on the left-hand side. And then down below, you can just see a sectional of a little box. And Spencer Axion his process was to take this blue thing as a plastic scintillator. And what he did was he wrapped them in foil, I believe. And then there's a SIPM, which is a detector that this scintillator is placed in front of that detector. I left this one on this side off so you could see the detector. And then there's a processing PC board on the back side that collects the data. And normally what I'm doing now is I found some paint that you can get at Home Depot that's silver mirroring paint. So I polish the scintillator and then paint it with mirroring paint. Put a little piece of tape over the area that I don't want painted for the light to come out. And then I put it in these 3D plastic printed boxes so I don't have to use electrician's tape to keep the light away from it. And then this whole thing will rotate and twist around and track the sun is the goal here. And then on the end over here, I've got another box. It's going to have 3 processors on it. There's a processor, an Adreno in each one of these little boxes here. And then there's going to be the Raspberry Pi over here. And the Pi will drive the motors and also collect the data. And it's got a Wi-Fi connection to it, so it'll feed it back into one of my servers just to, because these projects tend to accumulate quite a bit of data over time. So you want to try to be efficient, I found, with how you save the data and what you really try to save. And let's see, I think I have to stop sharing. Let's see if I can reshare and share that magnetic data. I think I picked the wrong one again somehow. It's coming up with the telescope thing, is it? Or did it come up with the magnetic data?
Now we see a graph.
You see a graph, right? Yeah, so this is an example of a 24 hours of data from the 3-axis magnetic sensors. And it shows you the transitions that happen at the different times as the Earth is rotating around. And you can look at these graphs and see some impact from activity on the sun, for instance, when it gets prominent, but it's quieting down from what it was about 6 months ago. But this is an older graph too. But anyway, that gives you an idea of what's possible. But that software is out there if somebody's interested in looking at the magnetic capabilities. And that's all I have.
Great. Any questions for Bob?
Yeah, I was just wondering about the muon thing. That sounds very interesting, but correct me if I'm wrong, but my understanding is that muons are formed in the atmosphere from the interactions of cosmic rays with the atmosphere, right? So these cosmic rays, they are essentially very highly accelerated charged particles, but because they are charged, they of course are going to be their course is affected by magnetic fields, such as the Earth's magnetic field. So how do you know that you are actually if you're pointing at the sun, that the muons that you are detecting are actually coming from the sun and not from some other direction and being influenced by the Earth's magnetic field or the interplanetary magnetic field?
Okay, Edward, that's a very good question. And that's the idea of stacking multiple simulators in a line so that a particle would have, or a neutron particle or muon would have to flow through your line, but your line has a very wide aperture because the simulator is a fairly large block, right? So if you just set it on the table and let it be stationary, you're sort of like doing drift scans. And the sun, you're not oriented relative to the sun at all. And that's why I decided to try to have the two stack block pointed towards the sun. And a key thing that I'm also recording here is the time of the time that the muon passes through each of the 2 simulators. And I've got an accuracy of about 200 microseconds resolution, but the time pulses are they're stretched out in the milliseconds because of a sample and hold detection scheme, so that I can try to correlate when a muon passes through both of the scintillators. And then by pointing at the sun and tracking the sun, and then pointing away from the sun at other things, I should be able to differentially compare what's coming from someplace else and what's coming from the sun. That's my goal anyway. I don't know
Okay,
how
so
it's going to work until I really start collecting data, but
so basically, like even if like the paths of the actual muons are like not completely straight due to like the magnetic fields and like how these cosmic rays are like basically like affected by this, because like the beam that you have essentially with is fairly wide, you should still be able to pick something up.
yes. Let's say you have a dish and you're picking up RF energy and you stack two of your dishes, you know, maybe 10 feet, one in front of the other, then you're going to improve your resolution in the forward direction. If you have to have a signal, if the signal has to hit both of the dishes.
Yeah, I understand that part. I was just like thinking about like the parts like before that, like the actual paths of like the cosmic ray particle where the muon originates from, because that's not going to be like a straight line like a radio wave. It's going to be like kind of twisted by the magnetic fields or.
Well, my understanding is that the cosmic ray hits a particle and then it
Yeah,
creates the muon. And so
yeah.
that transition can actually happen very close to the scintillator or in the scintillator potentially. And so, yeah, there is a sort of a scattering, but still there should be some statistics to this if the source is coming from a single direction. If the primary source, it comes from multiple directions, even from the Earth, but or through the Earth, but the sun is supposedly the biggest producer. And then there's also some controversy about whether or not T Cora Borealis will produce a lot of cosmic rays or particles, but I've heard some lecturers, professors give their thoughts that they will, and I've also heard that it won't. So, and it could be that it begins to do that prior to the eruption or the supernova event. It could increase prior to that. So it's supposed to happen anytime. I need to hurry up though, because it could happen before I get this working.
Okay. Any other questions for Bob? Great. Let's see. Anybody else I've missed? I've got N1LS still there. Anybody else?
Yeah,
All
this
right.
is N1LS. I'm just listening and watching all the presentations, enjoying them. Thank you very much.
Oh, thanks for coming on.
Thank you, sir.
Let's see. That's all I've got. Go ahead and look at there's a couple things. If you want to volunteer to be I need an assistant treasurer and we need a secretary and we need one more board member at least. And you can have more, but we can have more nominations for board members and we'd have to have a real election. But right now we got the three out of the four that will be reapplying. And then we need one more to fill out the board membership. And the election will start probably the week before the conference, and it'll end during the conference where they'll tally the final votes. So that's the time frame. All right, thanks everybody, and I'm going to leave I'm going to stop recording and leave this system on for anybody who wants to have a chat. All right, bye.